Okay, so we're going to get into the last section of the semester here, which is going to be 3-7. So again, keep in mind, we're looking at 3-7 over the next couple days. We'll review, we'll take a quiz over 3-4, 3-5, 3-7. Then we're done with chapter 3, so we'll review and take the test. And then if that, we'll review and take the exam, and that'll be pretty much the end of the semester here. So what are we dealing with here? Transformations of polynomial functions. The goal is I can identify symmetry and transform polynomials. All right, so the first little thing here is kind of a little introduction activity type thing to look at sort of what happens with these. So down here we have x squared. We're pretty familiar with that. And we've got x cubed. Hopefully you're pretty familiar with that too. It says, is a graph of f or g, so this is the f function, this is the g function, is a graph of f or g symmetric about the y-axis? So y-axis right here, we've learned these are definitely symmetric on the y-axis, whereas this one wouldn't be, because if you flip this on the y-axis, it would be like this, and it wouldn't be the same thing. So in this case, I'm just going to circle f. I'm going to say f is symmetric about the y-axis. Then it says, is the graph of f or g symmetric about the origin? You may remember that from geometry. If you don't, symmetric about the origin is just another way of saying 180-degree rotational symmetry. So that's saying if you rotated the graph 180 degrees, would it still look the same? The really easy way of doing that is if you just flip your paper or your screen, whatever you're looking at, if you flip it upside down, you can see if it looks the exact same. So this one, hopefully pretty obviously, if you rotate 180 degrees, is going to be pointed down here. And that's what you would see if you flipped it over. So then this would not be the same thing. So f is definitely not symmetric about the origin. This graph, on the other hand, though, is. If you rotate this 180 degrees, it's going to land in those same quadrants. And again, if you take a paper and you flip it over, you see that function is identical. So in this case, the takeaway is that g is symmetric about the origin. All right, then the last question on this part says, look for relationships. Graph more functions of y equals x to the nth, so like x to the third, fourth, fifth, sixth, so on, where n is a natural number. Which of these functions are symmetric about the origin, and which are symmetric about the y-axis? So if you remember what we did way back in like section 3.1, we did this, and we looked at different functions, and we looked at like x to the fourth, and we saw that, let me put my screen normal here. So x to the fourth looks a lot like x squared. And if you remember, so does every even function. If we go x to the sixth, same deal. These are always going to have y-axis symmetry. So I would say that when n is even, you're going to get y-axis symmetry. And then, as you can probably expect, whenever your power is odd, so let's say fifth power, it's going to have this kind of swoop type of look here, but it's always going to be in quadrants 1 and 3. All of these are 180-degree symmetry. So same thing's going to hold whether you make it 7, 9, 11, whatever. They're all going to keep that same shape. So they're always going to keep that 180-degree symmetry. So if n is odd, that's going to have what we're going to say symmetric about the origin, or origin symmetry. Okay, so that's kind of the general rule here of how these work. Now this leads us into a new phrase here, which is, kind of makes sense. It's what they call odd and even functions. So it's kind of a new term. So it says, this is an even function if it's symmetric about the y-axis, which is what we were kind of saying. When our n was even, we had y-axis symmetry. And then an odd function has origin symmetry, symmetric about the origin. So they're just saying that those are actually terms. They're called even and odd functions. Now, a function doesn't have to be even or odd. It can also be neither. So this is what you got to be careful about. You're really only going to get even functions when it is symmetric about the y-axis. So imagine if this graph was shifted like left a couple units. Well, now it's no longer an even function because it doesn't have y-axis symmetry. It'd have like, x equals -2 symmetry or something like that. So it does have to be right on the y-axis for it to remain an even function. So it's not just, hey, I see an even power, boom, it's an even function. That's not necessarily always true. They also give you a nice little rule here, which we'll use in just a second, but we'll hold off on that. Odd functions have 180-degree symmetry. They've got a little rule here. We'll come back and talk about that in a second. And then again, a neither function is one that doesn't have y-axis symmetry, But also, if you turn this 180 degrees, it's not the same exact graph. It's like now it's over here as opposed to being over on this side. So those are really your three possibilities. It's going to be an even function, an odd function, or neither. And you can just tell by looking at it graphically. All right, so we're going to come back and look at these rules in just a second. So it says use the graph to classify if it's even, odd, or neither. And this should be pretty easy. So right here, we've got this function. Obviously, it doesn't have y-axis symmetry. It does look like it has a 180 degree. You can always kind of flip it to double check. But basically, if it's in quadrants 1 and 3 like this, it's going to remain in quadrants 1 and 3 when you flip it. So this one is going to be odd. This has y-axis symmetry, so it's going to be even. Sorry, I don't know if you could see that on there. But anyway, this one, no y-axis symmetry. Also doesn't have origin symmetry. If you notice, it pretty much has to actually go through the origin in order for it to have origin symmetry. That's kind of a key point, so it's named that way. But this one, when you flip it down, well, now it's going to be crossing down here. It's not going to be the same thing. So this is an example of a neither. Okay, a couple more examples here. This one, so this is like a negative x cubed, but still, if you flip this, it's in quadrants 2 and 4. When you flip it, it's going to be in quadrants 2 and 4. So this is still going to be odd. This has y-axis symmetry, so it's still going to be even. Okay, so graphically, not very tough. You're just looking for either type of symmetry. It either has the symmetry or it doesn't. So now, when you're just given the function, okay, yes, you could graph it, but there's also a way to do this without graphing it, and that's where these little rules come into play. So if we look right here, the two rules are based on you evaluate the function at f of negative x. So you do f of negative x, you do f of negative x, and if when you do f of negative x, the function doesn't change at all, stays the exact same, then it's even. If you do f of negative x and you end up with a function that's the complete opposite of the original, then it's an odd function. And if you do f of negative x and it's neither of these two things, then pretty obviously it's a neither. Okay? So let's take a look at one of these examples and do it. All right, so for this function, we're going to evaluate, we're going to come up with what is f of negative x? What is that equivalent to? And then we'll decide whether it's odd, even, or neither, and you'll see how this works. So we're just going to, anywhere there's an x, you're going to replace it with a negative x. So this would be 4 negative x to the 4th. And all you're really looking to do here is to see, is that negative going to stick around or is it going to go away? And anytime you have an even power, any negative to an even power is going to become positive, because like a negative number squared becomes positive. A negative number to the 4th becomes positive. A negative number to the 6th. So as long as you have an even power, this is going to essentially just go away. And this is going to be equivalent to 4x to the 4th plus 5. So in this case, when we substitute a negative in, it doesn't change the function. It's still exactly equivalent to this one. And so the rule was, if the function stays the same, when you plug in negative x, it's the same as the original, then it's even. So we would know this is an even function. Okay. Also, you can check it graphically and see the same thing. I'll show you on this one. We'll probably won't do every one of them graphically because we don't really need to. But if you were to graph it, you'll see it's got an even power, so it's pretty obviously probably going to be even. But you'll see it's just the same graph shifted up 5 units. So yeah, it's got y-axis symmetry. Again, don't just see like, oh, it's got an even power, so it has to be even. Because depending on what you do to the function, if you mess with different things in here, different adding and subtracting type things, it can sometimes be a neither. Now, this one is definitely never going to be odd because the leading power is an even. So right away, you're like, this is even or it's neither. Those are the only possibilities by just looking at it. So same thing here. This is to the 3rd power. So this is either going to be odd or it's going to be neither. There's no way it can be even because the lead power, the degree, is odd. So in this case, let's do the same thing. We're going to do f of negative x. We're going to see how that shakes out. So 2 times negative x to the 3rd plus 3 times negative x. So in this case, this is an odd power. Odd powers are going to make the term stay negative because you're going to have a negative times a negative times a negative. So overall, it's going to be negative. So this is going to be negative 2x to the 3rd. And same thing here, this is going to be a minus 3x. And so what we notice happens in this one is you take this function, if you make everything the opposite, you get this one. And that's that second rule. If when you do f of negative x, you just get the negative function, you get everything is opposite, then it's an odd function. So in this case, we get an odd. So there's an example of like both types just kind of working out and playing out. Now, as you do this, what you might notice is the times where it's going to be neither are when you have mixtures of odds and evens. So let's look at the next example on here. So if we look at this one, so right away, we see the lead power is odd. So this is either going to be odd or it's going to be neither. So we jump to our test and we do f of negative x. And we see, so we have 7 times negative x to the 5th minus 2 times negative x squared plus 4. And so what happens here is the negative to an odd power is going to stay negative. So you have a negative 7x to the 5th. But now we have a negative squared. So this is going to keep its sign. It's because the negative is essentially just going to cancel out because it's an even power. So this is minus 2x squared and then plus 4. And if you compare this to the original, it's not identical because those signs are opposite, but it's not completely opposite either because that one flipped, but these two stayed the same. So because of that, this one is a neither. It doesn't fit either rule. Okay? And so you're going to kind of notice a pattern here. And the pattern pretty much is if it's got combinations of odds and evens, then it's going to end up being a neither because you're going to get your signs not flipping or flipping and so on. So let's look at this last one. So let's go jump right to our rule. So this would be negative x to the 6th minus 2. Since it's an even power, it's going to be equivalent to just x to the 6th minus 2. So you see these are the same, and when they're the same, it's even, which is what we would kind of expect going in because it does have a even degree. So it can be even or it can be neither. In this case, it ends up being even. So again, not that tough, but you have the rule to check these. You also have the graph to check these. Either of these you could graph and see that, oh, yep, that has y-axis symmetry. Oh, that one doesn't have either type of symmetry. And that's it. So that's your odds and even functions and the trends you got to see with those.